All right, what's one thing we know about equilibrium? Yes? Forward rate equals reverse rate, yes. It's another thing we know. Yes? Has to be a reversible reaction. It's hard for the reverse rate to equal the forward rate if there's no reverse rate. What else, Baran? No observable changes. What else we got? Joanne? Has to be a closed system. Yes? Yeah, Gibbs free energy equals 0. Nice. That's AP only. Regular chem says Gibbs. What's that? Okay. Yes. Constant temperature. Yeah, temperature must be constant. Anything else anyone wants to add to that list? That's pretty good, I think. Yeah? Okay. So today we are going to look at coming to equilibrium in terms of rates. And this is on page 5, 2.1b in the pink book. Okay, so we have our reversible reaction. That is, it comes to an equilibrium. Most chemical reactions look like this. We have a one-way arrow. And if you have carbon reacting with oxygen, that is a simple combustion reaction. CO2 will not break down into carbon and oxygen. So lots of reactions are one way, despite the fact that for the next 4 units, we will be discussing almost exclusively reversible reactions, okay? So most reactions are actually one way, but there are lots of others that are like this one, where they go both forward and reverse. And when we have that forward and reverse, we use the double harpoon arrow. And if you're wondering what a harpoon is, it's one of those things that they used to use to stab whales back in the whaling days. Kind of nasty, but you know, there we are. History is often quite nasty. All right, so we have our forward. The top arrow is the forward and the bottom arrow is the reverse. I got a little carried away with finding images of harpoons. It was very exciting for me. Anyway, there we go. So the top arrow tells us that ammonium chloride can break down into ammonia and hydrochloric acid, and the reverse arrow, the bottom arrow, tells us that they can come back together to form ammonium chloride. So we call this one the forward reaction, and we call these the reactants, and we call these ones on the right-hand side the products. Now we have also the reverse reaction, and we still call the stuff on the left-hand side the reactants, even though in the reverse reaction, those reactants are being produced, okay? And we call the stuff on the right-hand side the products, even though the products are reacting, okay? Just always whatever is on the left is the reactants, whatever is on the right is the products, okay? It just gives us, if you started changing the names of them, it would just get too confusing. Do you know what I mean? Like if you were like, okay, these are the reactants for the forward reaction and these are the reactants for the backward reaction. It's just nice. It'd be better if we had some other terms that were completely unrelated to that, but we don't, so there we are. All right, both of these reactions occur, then we have a reversible reaction. It is important to understand that even though we are talking about an equilibrium mostly where the forward and reverse rate are equal, the forward and reverse reactions can take place at different rates. It's just if they take place at different rates, then they are not at equilibrium. So if the forward rate does not equal the reverse rate, we are not at equilibrium. EQM, guess what that stands for? Equilibrium. All right, so what we're going to do is we are going to take some NH4Cl, some ammonium chloride, and we are going to place it in a closed container, because remember, we need to have a closed container to reach an equilibrium. And all we're putting in there is NH4. We have not put in any NH3. We've not put in any HCl. So we've got loads of this. We've got tons of this. And we have none of the other stuff. So what that means is that if we have loads of the NH4Cl, what can we say about its rate of decomposition? If we have lots of it, it is high. So we have a fast forward rate. What can you say about the reverse rate at the very beginning when we put in NH4Cl and we don't have any NH3 or HCl? There is no rate. It's zero because you cannot have a rate if there's nothing reacting, okay? So our reverse reaction, we have none. The rate is equal to 0. Okay, because we got nothing. So that's at the very beginning. And if we graph these, and we're going to put our rate in molar per second on our y-axis, and we're going to put progress of reaction on our x-axis, the initial rate of the reverse reaction is at 0. The initial rate of the forward reaction is fast. Okay, so they start out far apart. Are those two equal? No. Are we at equilibrium? No. All right. So here we are. We are making NH3 and HCl. That is fast. And we are also using up NH4Cl fast. We are not making any NH4Cl, and we are not using up any NH3 plus HCl. So let's use this to choose the following responses. Are we using up NH4Cl faster or slower than we are producing it? We are using it up faster than we are producing it. So what will happen to the concentration of NH4Cl? It's going to decrease because we're using it up faster than we're making it. So will there be more or fewer collisions between NH4Cl molecules? There will be fewer. And if there are fewer, then what is happening to the forward rate? The forward rate will decrease. All right? Now, in the other instance, we have NH3 and HCl, our products. Are we producing them faster or slower than we are using them up? We are producing them faster than we are using them up. As time goes on, will the concentrations then increase or decrease? They will increase. So there will be how many collisions? More. And that means the reverse rate will? You got it. Okay? All right. So what is that going to look like in our arrows? Normally, we don't draw arrows with different sizes, but when we're first starting out learning about equilibrium, we'll show the process where we have our forward rate as being faster. We'll show that with a bigger arrow. Okay, so it's still fast, but not quite as fast as it was before. And now we have the reverse rate, which is also occurring, but it's not too fast yet. On our graph, what that's going to look like is that the forward rate is still fast, but not as fast as it once was. And our reverse rate has sped up from 0. Now it is something. So now we are on our way to equilibrium. We are fastishly making NH3 and some HCl, and we are using up NH4Cl, and we are slowishly, so fastishly making those and using that, we are slowishly making NH4Cl and using up that should say NH3, not NH4. Fix. Okay. Use the above reaction to choose the correct responses. At this point in time, on our way to equilibrium, are we using up NH4Cl faster or slower than we are producing it? Faster. So, NH4Cl concentration will decrease. So there will be fewer collisions, which means that the forward rate will decrease. Oh, shock. It's the same thing as was happening before, just again. We are producing NH3 and HCl faster than we are using them up. Therefore, as time goes on, NH4 and HCl will increase. And so there will be more collisions, which means the reverse rate will increase. And what's that going to look like on a graph? It's going to look like that. And the same thing will happen over and over and over again. Like it'll keep, the forward rate will keep getting slower and the reverse rate will keep getting faster until what's going to happen? We're going to reach an equilibrium. And at equilibrium, what should happen with those dots? They should come together and line up. Okay, so what we're going to do is we're going to draw smooth lines connecting the dots of the two curves, and we are going to carry that line on. So I'm going to do the top one in black. And I'm going to do the bottom one in red. Oops, this should have gone a little bit. I did not do a good job. Let's try it again. Better. By the way, if you suck at drawing straight lines, when it comes to equilibrium, use a ruler. Yes? Okay, I have rulers, so if you're on a test or a quiz, make sure if you suck at drawing straight lines, if your straight line looks like this, that is not a straight line, use a ruler. Okay? So, at what point have we come to equilibrium? Where the two meet. We have reached equilibrium. The two rates are equal. This is our forward rate. This is our reverse rate. All right. I'm not going to have you watch this video because it's just really a review of what we have done, but this is a review video should you want to watch it in the future. And that takes us to our exercises, which we're not going to do right now. 2.1c. Position of the equilibrium. Again, this is going to be a review video. We're just going to do it without the video for now. When last we left our system, in the last thing, the forward rate was equal to the reverse rate, and the system had reached equilibrium. But it is important to realize that at equilibrium, both reactions are still happening. Okay, they haven't stopped. The reactions don't stop. They are still happening, but the forward rate and the reverse rate cancel each other out. What do we mean they cancel each other out? We mean, let me see how I phrased it for the other class, because I did a fairly good job there. Let's see. There we are. Yeah, that's what I thought. Okay. The reactants, for example, are being used as fast as they are being produced at the same rate So reactants are being used at the same rate as they are being produced. Therefore, what can we say about the concentration of the reactants? Yeah, concentration of the reactants will remain constant. Just like in the video you hopefully watched yesterday or on the weekend, where if you got one person digging a hole and the other person filling it at the same rate, you don't end up with any change in the size of the hole. It just remains the same. Okay, and it'll be the same for the products. However, just because the concentrations won't change, just because they are constant, does that mean that the concentration of reactants is equal to the concentration of the products? No. Okay, concentration of reactants does not equal concentration of products. I'm going to get rid of that too. There we go. Any questions about that? We good? Okay. So, for example, at an equilibrium because any system can have many different equilibrium positions, okay? One of the things about an equilibrium, if you recall, is that the conditions have to be constant. What if we start changing the conditions, we're going to start changing the equilibrium, okay? But at an equilibrium, this is at constant conditions, in this particular case, we have a small amount of reactant. You can see it's small. And we have a large amount of product. However, under different conditions, we might have a different equilibrium where we have lots of reactant and we have very little product. And we're going to learn some language around that. Okay, so this is also an equilibrium at different conditions. Same system, different conditions. Maybe it's a bigger container, maybe it's at a different temperature, that kind of thing, okay? What we say is if we have more products than reactants, if the concentration of products is greater than the concentration of reactants, we can say two things. We can say the products are favored. The second thing we can say is that the position of the equilibrium lies to the position of the equilibrium. And by the way, position, P-O-S-N, position, okay? The position of the equilibrium lies to the right or left? Right, yes. Sorry, I just didn't hear you the first time. So the products are favored, the position of the equilibrium lies to the right. So we're just going to practice that language a lot, okay? If, on the other hand, the concentration of reactants is greater than the concentration of products, what could we say? We could say that who is favored? Reactants are favored. And we could say the position of the equilibrium lies to the which direction? Left. Excellent. Is good? Okay, excellent. So summary, just because the concentration of products and reactant remain constant at equilibrium, that does not mean that the concentration of products equals the concentration of reactants. The relative concentrations of products and reactants depends upon the conditions. So here we have this one, and this just reiterates. I guess I got ahead of myself because we're doing the lies to the right. Here we have the position of the equilibrium. We got more products than reactants. It lies to the right. Our products are favored. We have more reactants than products. We've got reactants. I've switched colors. That's bad. This should be blue. So at least I'm consistent between my blocks. You guys probably don't care, but I do. Lies to the right, products are favored. And if we have more reactants, the position lies to the left and the reactants are favored. So let's look at what happens when the conditions change. Okay, so on our left-hand side here, we have a system is at equilibrium. Okay, that's what we're starting with. We have our initial equilibrium here. And what can we say about that equilibrium? Our initial equilibrium, how would you describe it? Yeah, the position lies to the left. And what else could we say? Reactants are favored, yeah. No, I'm drowning you in the language so that you're like, okay, favored, yeah, reactants, yeah, position lies to the left. We're just kind of overusing the language so it becomes really familiar. Okay? Just use one. Now, what do we do next? We're going to add some heat. In other words, we are going to increase the temperature. So 1, we have our initial equilibrium. 2, we increase our temperature. That is a change in condition, yes? We started with lots of reactant, and then when we heat it, this is after heating, what did we end up with? We ended up with lots of product. Okay, so after heating, this is our higher temperature. We have a new equilibrium. Now, because we started with more stuff on the left and we ended up with more stuff on the right, we say that the equilibrium has shifted its position. Yes? We shifted from being left focused to being right focused. So we say the equilibrium shifts to the right.
When you say position lies to the left, just mean the concentration of the products is high.
Yeah, so if the position lies to the left, the concentration of reactants is higher.
Yeah.
Yeah.
Then if this one's right, the products.
Exactly. So here the concentration of reactants is greater than products. And over here on the right-hand side, we have the concentration of products is greater than reactants. So the position lies to the right. Please correct me if I ever get it backwards, because often I'll be like the reactants and then you shift to the right, but you have to remember that's my left. So I sometimes mess it up and say what mine is. So I try, but I don't always get it right. And sometimes I just get it wrong because my brain just does left and right wrong. Okay, and our products are favored. So 1, we have our initial equilibrium. 2, we change the conditions. 3, the thing shifts to the right. And 4, we end up at a new equilibrium. What has to be true of the 2 rates during the shift? In order to get from more reactants to a position with more products during the shift, are the forward rate and reverse rate equal? No. Which one is faster during the shift? The forward rate is faster. That allows us to make more products and use up reactants. And I'm going to get a little ahead of myself now. If we increase temperature, what happens to rate? Increases. So when I increase the temperature, what happens to the forward rate? It increases. If I increase temperature, what happens to the reverse rate? Increases. But we know at some point the forward rate is bigger than the reverse rate. Have a chat with your neighbor. How is that possible when I just increased both rates?
Forward rates to be greater than the reverse rates. It has to go to I feel like the concentration of liquid is low, is high. That's why it's staying still.
All right, so here's my forward rate, here's my reverse rate. The 2 are equal. Yes, forward rate, reverse rate, equal. Now, I increase the temperature. What happens to the forward rate? It increases. What happens to my reverse rate? It increases. But do you see how one can increase more than the other, so the forward rate ends up being faster? So what we would have here is we would actually have, if we were to draw our equilibrium arrows to kind of show the difference in the rates. By the way, we don't normally do this like on tests or whatever, but it is useful for illustrating. At our original equilibrium, we would have our forward rate and our reverse rate. And then while we are shifting, we'll have our forward rate and our reverse rate. They're both higher than before, right? Our increase in temperature sped up both rates. And then when we are finished, both rates will be bigger than they were before. So everything's faster, but now they're equal again. Does that make sense? Cool. Okay. And like I said, I'm getting ahead of myself with that. We're going to talk about that way more later. So if that didn't make sense to you yet, don't worry about it. We'll hit it again. All right. Now, guess what's going to happen if we cool the system? Well, if we decrease the temperature, so we have, thank you, for sure. We have our initial equilibrium. And number two, we decrease the temperature. We have changed the conditions, so what happens? The equilibrium will shift. In this case, which direction does it shift? It shifts to the left. And then after we have finished shifting, we get a new equilibrium, okay? And basically what's happening there is both rates are slowing down, but one of them slows down more than the other, right? So we start with our rates being the same. When we cool it, both rates slow down. Which rate slows down? Which rate is faster if we're shifting left? The reverse rate. But it doesn't mean it's faster than it used to be. It means it's faster than the forward rate, but it is still slower than it was before, right? Maybe I should make these ones bigger. Okay, it doesn't matter. And then the forward rate is even slower, right? And we end up then with a forward rate and a reverse rate that are both smaller than before. So when we say shifting, it's when it moves from one equilibrium position to another equilibrium position and the forward rate does not equal the reverse rate. During the shift. So systems shift in response to a change in conditions. I'm going to introduce another word that we will come across soon enough. And a change in conditions in this unit is referred to as a stress. While the system is shifting, the concentration of reactants and products change. But when you are finished shifting, what will happen with the concentrations? They will remain constant, and you'll have a new equilibrium. Okay, closed systems. Regardless of the position of the equilibrium, equilibrium can only be reached as long as we are in a closed system. What is a closed system? Yes. No gas can escape. Okay? So matter is not allowed to go in or out. In this case, we've got a little picture here. Mass, which is matter, is not allowed in or out. But what is allowed in or out is heat. So you can affect a system by heating it from the outside or by putting it into an ice bath and cooling it down. All right. In an open system, you can have mass transfer in and out, but heat transfer, no. A closed system does not mean you have to have a stopper on it. If you have a gas, yes, it means you have to have a stopper on it. But what if you had a double replacement reaction? You've got aqueous and aqueous gives you aqueous and solid. Is anything escaping that system, that aqueous area? No. So that is also a closed system, even though you don't have to put a lid on it. It can just be in an open beaker because there's no gases to escape. They are stuck in, like the solid is stuck in that beaker. The ions are stuck in that beaker. You wouldn't want to leave it for too long, otherwise the water might start evaporating and that's going to change concentrations. But it would be, for a short term, be totally fine. Okay, so you have to have none of the reactants or products able to escape. So closed systems do allow for the transfer of heat, which can lead to the shifting in the position of the equilibrium. Okay. The last thing we need to cover is that for every reversible reaction, they are always exothermic in one direction and endothermic in the other direction. Does that make sense? If we have our little potential energy diagram, and in the forward direction, let's say it's exothermic, in the reverse direction, it would have to be endothermic. Like if you're reading it forwards and backwards, they have to be opposite of one another. Okay? Do you remember last year we did a lab with hydrated copper sulfate? This is called a hydrate. See if you can remind your neighbor what a hydrate is. What's a hydrate? Yes. A crystal lattice with water in it. So here we have a crystal lattice. What type of crystal lattice is this? Ionic. Okay. You can actually have anything that has a regular pattern as a solid would be a crystal lattice. So if you had I2 stacked on top of I2 stacked on top of I2, I2 is a molecule. So that would be a molecular crystal lattice. Anytime you have a metal and you've got copper, 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 and they're all stacked nice and neat and tidy, that is a crystal lattice. That would be a metallic crystal lattice. But mostly we are concerned with ionic crystal lattices. Okay? And you'll notice there are spaces in there. And we can put into those spaces some Where did my yellow one go? The yellow one was fun. Oh. You might be able to guess what happened to the yellow one, if you know me. All right, so we got our water molecule. See that we got the O here and the two H's. Kind of is a decent model for water. Decent, available, and cheap, okay? And I only have two hands, so I can only do two water molecules, but you can imagine they are so small, they can fit in the spaces in the crystal lattice. And now we start to heat it. When we heat it, what happens? They start to jiggle around. Now, what is holding the ions to each other? Ionic bonds. Are those strong or weak? Strong. What's holding the water inside the crystal? IMFs, intermolecular forces. Are those strong or are they weak? They are weak. So as this jiggles and as these start to move faster and faster, what will eventually happen? The intermolecular forces will break and the water will boil away. Okay? Was that an endothermic or an exothermic process? That was endothermic because we had to heat it. We had to put heat in. Okay, so that's what's happening here. We have our hydrated copper sulfate, which we can write the formula for. That is, do you guys remember Cu, copper sulfate, copper 2 sulfate, CuSO4. How do we write the formula of a hydrate? What do we need to put next? We put a dot, and then there are 5 waters per 1 copper sulfate. And then if you recall, the name of the dehydrated salt is not called dehydrated, it is called the anhydrous. An meaning without, anhydrous copper sulfate, which is just CuSO4. And of course, we have water. What are the states? CuSO4.5H2O, what state is that? That is a solid. What state is the anhydrous copper sulfate? Solid. And water, of course, is a liquid, although when you heat it, it comes off as a gas, so I would probably put it as a gas there, okay? What color was the copper 2 sulfate? It was blue. Do you remember the color of the anhydrous copper 2 sulfate? It turned a super exciting color, like gray, white, okay? Okay, so it turned from blue to white. At the end of the experiment, did you drip some water back in? What happened to the color? Perhaps we have forgotten, yes? Okay, it turns back to blue. If you were to touch the side of the test tube, like let's say you made your anhydrous salt, okay, and you let it cool down so that you're not, it's just cool now. And then you put the water in, it turns blue. What would you expect to feel when you touch the test tube? Have a little chat about that. What would you expect to feel when you add the water back in?
It says it was killed. It says it was.
I think you guys are both saying the same thing, just coming at it from different directions, right? Yeah. So we have bonds forming. We have those IMFs forming. I've lost my water again. So here's another water. Okay. The water comes in and it forms. All right. Those IMFs form. And so it is exothermic. But also because this was an endothermic process, this has to be an exothermic process. So you can approach that logically from either of those kind of two ways. All right. So reversible reactions can proceed in both directions. One of the directions must be endothermic and the other will be exothermic. And at equilibrium, the rates are the same. The forward and reverse rates are the same when we are at equilibrium, and the concentrations do not change. However, products concentration does not equal reactants. It has to be in a closed system, and the position of the equilibrium can change and will shift to the right or left depending upon the conditions. And that is it for today. That's as far as I got. Yes? They can be. It's just unlikely. Do you know what I mean? It's like, yeah, it's just, it would randomly happen that way. Yeah? So, yes, it could happen. That concentration products equal concentration of reactants, but it would be a very unlikely happenstance. Ooh, I like that word. Yes. Yes. So stresses can be changes in concentration, changes in volume, changes in pressure. Yeah. Yes, it could happen, but it would be a very unlikely. I will say circumstance because I think maybe that's a better word. I like happenstance better though. It's just a better word. It's more fun. I was so happy. Somebody on one of the tests or quizzes used the word whilst. I was so happy. I assume they've been reading my chair, or they came across it somewhere else entirely. But anyway, it made me happy. I like words. All right, and that is it for that. Your homework, which you can work on for the next 15 minutes, is... Where did it go? In the blue book, page 13, pages 24, 25, page 31, and page 38. And you got 15 minutes right now, and if you want to work on it during flex, you also have another 20 minutes then, so I would advise getting that done because it is a fair bit. Blue book.
So instead of that, it says like an organized structure.
Yes.
So I got ice.
Yeah.
Reorganized solid.
That is a molecular crystal. Yeah.
Is that? Is it hydrated or
No, we can't hydrate water. You know what I mean? Yeah. You can have certain other solids which are hydrated. Like think about brown sugar. Just that's hydrated.
Yeah.
Yeah.
It's just sugar.
Yeah. So it's not impossible to have a stick entirely to
No.
Yeah. It was so funny. When I went through my school, I loved my office. And I liked but Then I got to teach chemistry and I'm like, more than biology. But I love the biology. Get those lines. Do you get tested on the blue book? I can give you a practice test on the blue book. Yeah.
So this is all the extra stuff. Yeah, there's like a whole one. And she's not. Yeah,
All right, we are not playing on our phones. You can take pictures, absolutely. We are opening our blue books. Unless it's something because I understand it. Okay. Like honestly, like I get it. There are times we just.
Yeah.
Yes, no, I hear you.
Yeah, it moves. Because we have to learn how water gets there. And we were also deriving integrating the Navier Stokes equation.
And God bless you guys, none of you asked me if your tests were marked. They are not. If your tests are marked, I will be like, yeah, your tests are marked. I'll be so proud of myself, right? I won't be able to contain it. But it won't happen for a while. Thank you. No problem.